What we're about to go over right now is the Muon experiment. And the Muon experiment is a demonstration of time dilation and length contraction. So this is a demonstration of relativity in action. So what is a muon? A muon is an elementary particle similar in nature to the electron. It has a half-life of 1.56 microseconds, or 1.56 times 10 to the minus 6 seconds. And for the purposes, in general, we say that it travels at 98% of the speed of light, something around 98 to 99% of c. Its v is 98 to 99% of c. But for the purposes of our video, we're going to use some simplified values to ease our calculations a bit. We're going to say we have 2 times 10 to the minus 6 seconds, and we're going to say we're traveling at 99.99% of c. So we can see some of the exaggerated effects that are slightly easier to calculate. Now, what we say in this experiment is a muon is formed 10 kilometers above the surface of the Earth, 10 kilometers above Earth's surface. Now, what we find is we want to calculate how far does it travel. Does it reach Earth? Does it reach Earth? So, we have our distance equals time times velocity. So we put that in. D equals 2 times 10 to the minus 6 times 99.99%. So what we have is 0.9999 times 3 times 10 to the 8. Alright, does it reach Earth? So what we find is 2 times 10 to the minus 6 times 0.9999 times 3 times 10 to the 8 is around 599.94 meters. Now, 600, which is around 600 meters, over 10 kilometers, is only 6% of where we need to be. So the probability that it'll reach Earth is very, very low, the surface of the Earth. So how exactly do muons reach Earth? Well, experimentation not only suggests but also confirms that we've measured muon presence on the Earth's surface, that we've measured impactions between muons and the surface of the Earth. So how do we validate or confirm these experimentation, the results of this experimentation? Well, we know that relativistic speeds allow or facilitate for the effects of time dilation and length contraction. And these play an immense role in the travel of a muon. So its half-life, in being so short, prevents it from reaching Earth, or the surface of the Earth. So how do we know that they're here? Well, we start with time dilation. To a stationary observer, we'll split our page in half. We have a stationary observer on Earth. This scientist has the correct equipment to observe the muon, and the muon is moving at this velocity. So we have gamma, or the Lorentz factor, for this muon is 1 on 1 minus 0.9999 c squared on c squared. Right? And so we simplify that gets multiplied out, and that cancels, and we have 0.9999 squared, so y equals 1 on root 1 minus 0.9999 squared, and what we find is 1 on square root of 1 minus 0.9999 squared is around 70.7. So this is the amount of the proportion of time dilation, and we know that our dilated time is equal to our gamma times ordinary time or proper time. So we have our gamma stored here, and our time is 2 times 10 to the minus 6 seconds. Right? So we have 2 times 10 to the minus 6, and then gamma 2 equals, so you can rub this out, 70.7 times 2 times 10 to the minus 6 equals, 70.7 times 2 times 10 to the negative 6 equals 0.0, oh, that's an eraser, 0.0001414, or 1.414 times 10 to the minus 4 times 10 to the minus 4. Now this is a lot more time to travel. Do the muons reach the surface of the Earth? Well, let's rub this out. And remembering that this is time gets dilated from the perspective of a stationary observer to the relativistically moving object, or the object moving at relativistic velocities. So, with our new time, we have our distance equals, 0.9999 times 3 times 10 to the 8 times 1.414 times 10 to the minus 4. Does this reach the surface of the Earth? And this is in meters. 0.9999 times 3 times 10 to the 8 times our time, 1.414 times 10 to the minus 4. Minus 4, and we find that it travels 42,415.758 meters. Alright, and if we divide that by 10,000, we have, it's 424% of how far we need to travel. So these muons will definitely reach the surface of the Earth. However, to the muon, its half-life, or its lifespan, is still 2 microseconds. Time does not dilate from the perspective of the muon, because in fact our proper time, this 2 times 10 to the minus 6 seconds, our proper time is sourced from the muon. So time doesn't dilate for the muon. It dilates for that stationary observer. Alright? But length does contract for the muon. And length contracts both for the object in motion and the direction of length that it travels in, or the length of direction in which it travels. So, as our muon falls to the Earth with a v equals 0.9999 c, and this height is 10 kilometers, you know, this is just a little tiny graph, color in our muon. What we find is, remembering our equation for length contraction now, L prime equals L, proper length, times our inverted Lorentz factor, and our relativistic factor for this is 0.9999 c all squared on c squared. And we remember that this expression in the bracket, or in the radical sign, L prime equals L, there we go, 1 minus 0.9999 squared. And what we find is it's equal to square root of 1 minus 0.9999 squared is equal to, so what we have is our proper length is 10,000. 10,000 as measured from the observer. So proper time is measured from the object in motion. Proper length is measured from an object stationary to the start and end points of the journey, as well as the object in motion. So the scientist on the ground has measured 10,000 meters or 10 kilometers that this muon must travel to reach the surface of the Earth. And our factor in the radical sign is 0.01414, which, that's a recognizable sequence of decimals. There's a relationship between length contraction and time dilation. And what we find is 10,000 times 0.01414 equals, our contracted length is equal to 141.4 meters. Now, considering that the original non-time dilated, time t primed, non-t primed distance was around 599 point something, 0.5 around about, so 600 meters. 600 meters. Does 141.4 meters exist within that potential range of the muon? Yes, it does. Now looking at it, the muon under non-dilated time will exceed the range at which it must travel by 424%. That is 600 meters over 141.4 meters. 424%. A similar or the same factor by which it would definitely reach the ground under dilated time. And so not only is this a proof or a very lovely example of time dilation and length contraction, but it also establishes the symmetry in the numbers you get when you deal with time dilation and length contraction in the same example. So this was the Muon experiment. And that is all. Thank you.